Welcome to lecture 27. In this week, we have started our discussion on measurement of high vacuum or very low pressures. In the previous lecture, we have talked about measurement of low pressures by McLeod gauge. In this week, we will talk about another low pressure measuring instrument, and that will be ionization gauge. So, we have talked about McLeod gauge, and today we will talk about ionization gauge. So, today's topic is ionization gauge, which can be used to measure very low pressures or very high vacuum. The basic principles of ionization gauge is as follows. An electron passing through a potential difference will acquire a kinetic energy that is proportional to the potential difference through which the electron is passing. If this energy is large, an electron strikes a gas molecule, there is a possibility that the electron may knock out a secondary electron from the gas molecule, and in that case the gas molecule will be converted to a positively charged ion. Number of positive ions formed is dependent on the number of gas molecules per unit volume, and number of gas molecules per unit volume is a measure of pressure. Of course, the number of positive ions will also depend on number of collisions. So, number of electrons that are passing through the potential difference. But if I can keep the number of electrons passing through constant, then the number of positive ions formed will depend on the number of gas molecules present in the chamber, and number of gas molecules per unit volume is nothing but a measure of pressure. The pressure or vacuum can be measured by measuring the current produced by the ionized gas molecules. This current will be very small amount current, so amplification will be required for the purpose of measurement. So, let us look at this schematic. Electrons are passing through a potential difference. These are cathodes and anodes. Let us consider this is a closed chamber, and to that chamber the vacuum source is connected. So, you are measuring very low pressure of say a gas stream. So, there will be gas molecules in this chamber. Now, when the electrons passes through this potential difference, they will acquire kinetic energy which is proportional to the potential difference that is being applied. Now, if this kinetic energy is large and if the electron collides with these gas molecules, the gas molecule will be converted to a positively charged ion. Because this electron when collides with a gas molecule, and if this kinetic energy of the electron is very high, it can knock out a secondary electron, and then the gas molecule will be converted to a positively charged ion. So, number of this positively charged ion will depend on the number of gas molecules present in the chamber. Number of gas molecules present in the chamber is nothing but a measure of pressure. More number of gas molecules in the chamber means more pressures, very few number of gas molecules in the chamber means very low pressures. So, the basic principles of ionization gauge is that we have to emit electrons which will acquire kinetic energy, and those electrons will collide with the gas molecules whose pressure I am going to measure. After this collision, positively charged ions will be formed. I can measure the current due to production of the positively charged ion, and that current will be a measure of the number of gas molecules or the pressure. So, depending on how I ionize these gas molecules, I have different types of ionization gauge. I can heat up a cathode to draw electrons. I can impose a high magnetic field to draw out electrons. I can also use alpha particle emitters, making use of a radioactive source to ionize gas molecules. So, that way I will have different types of ionization gauge. I can have hot cathode ionization gauge, I can have cold cathode ionization gauge, and I can have Alphatron which use alpha particles to emit electrons. So, hot cathode ionization gauge will heat up a cathode to emit electrons. Cold cathode ionization gauge does not heat up the cathode. There I make use of magnetic field, high magnetic field, and then in Alphatron, there also we do not heat it up the cathode. What we do is we make use of alpha particles, a radioactive source to emit alpha particles which will ionize the gas molecule. Ionization gauge produces very small current which is about 10 to the power minus 12 ampere, and thus needs to be amplified. One good thing about ionization gauge is this, that the output of the gauge is generally linear. Now, this is the schematic of an ionization gauge. This is the cathode which is being heated up. So, an electron passing through a potential difference will acquire a kinetic energy that is proportional to the potential difference. If this energy is large and the electron collides with a gas molecule, the electron may knock out a secondary electron from the gas molecule, thus the gas molecule will be a positively charged ion. So, I have cathode and I have anode which is electron collector. Now, this cathode is heated up to emit electrons. So, that electrons goes to the electron collector. While it is doing so, this chamber is connected to the vacuum which I am going to measure. So, thus these electrons also collides with the gas molecules that are present within the chamber. When these electrons collide with the gas molecules that are present in the chamber, it produces a positively charged ion, and I use an ion collector and get the ion current. This ion current depends on the number of positively charged ion that is formed and number of positively charged ion that is formed will depend on the number of gas molecules as well as number of electrons present in the chamber, but I can set an electron current which will control the number of electrons being emitted. So, ultimately this ion current for a given ionization gauge will be a measure of pressure. So, number of positive ions or ion current depends on the electron current, that is number of electrons emitted by the cathode, and number of gas molecules. For a given gas and a constant electron current, ion current become a direct measure of number of gas molecules per unit volume, which is nothing but pressure. So, typically this is around 6 volt and this is around 20 volt. This is a photograph of commercially available hot cathode ionization gauge. Typical range of hot cathode ionization gauge is 10 to the power minus 3 to 10 to the power minus torr. 1 torr is 1 millimeter of mercury. So, the hot cathode ionization gauge can measure a pressure as low as 10 to the power minus 10 millimeter of mercury. This is how I express the sensitivity of an ionization gauge. See, sensitivity in general will be output by input. So, my output is ion current, which is I, that is how I am representing in the figure also. Input is the pressure P, but typically instead of expressing sensitivity of ionization gauge by II by P, that is ion current divided by pressure, we express the sensitivity of ionization gauge as ion current divided by pressure into electron current. So, that way the sensitivity value becomes independent of electron current. This is because different ionization gauge can use different electron current to emit electrons, and if you have different electron current means different number of electrons are being emitted. So, there will be different number of collisions between electrons and the gas molecules. So, there will be different ion currents. So, to make the sensitivity independent of electron current, so that I can compare the sensitivities of different ion gauges that are using different electron currents, we express the sensitivity of the ionization gauge as ion current divided by pressure into electron current. The sensitivity for an ionization gauge has a typical value of 200 torr inverse or 2.67 kilopascal inverse. The gauge cannot be used when the pressure is greater than about 10 to the power minus 3 torr, since the filament is likely to burn off. For the hot cathode ionization gauge, there is a possibility that the filament can burn off. So, we should never use the ionization gauge or hot cathode ionization gauge when the pressure is more than 10 to the power minus 3 torr. The vacuum space is provided with different pressure measuring devices such as manometer, Pirani gauge, etc., to ensure that the pressure is below 10 to the power minus 3 torr. So, before we actually connect the vacuum source with the hot cathode ionization gauge, we want to ensure that the pressure is less than 10 to the power minus 3 torr. So, what we do is we first connect to the manometer that can measure low pressures, or another vacuum measuring instrument known as Pirani gauge, which we will talk about later, and make sure that the pressure is less than 10 to the power minus 3 torr. Then we make use of ionization gauge to measure the vacuum. So, the hot cathode ionization gauge has a heated filament which is cathode. We have a grid with negative potential which is ion current, and this was the cathode which is being heated up. This is the grid which captures ion. So, it has a negative potential, and you have an anode which is positively charged and electron collector. The filament is typically made of thoriated tungsten or iridium. There are certain gauges which has two filaments. In that case, one is usually spare or standby. Thoriated tungsten means you have thorium in tungsten, filaments made of tungsten. Due to high temperature, the filament may burn out and the cathode may get oxidized. The hot cathode ionization gauge is not suitable if the gas whose pressure is being measured is decomposable. Since we will be using high temperature to emit electrons from the cathode, if the gas whose pressure is being measured is decomposable, it is not suitable, as it may lead to undesirable reactions. Next, let us talk about cold cathode ionization gauge. This is also known as Penning gauge. Penning was the inventor of cold cathode ionization gauge. As the name suggests, in case of cold cathode ionization gauge, there is no heated cathode. So, we do not heat up the cathode to draw out electrons. Here we will make use of high magnetic field. So, the indicative range of cold cathode ionization gauge is about 10 to the power minus 5 torr. This is 10 to the power minus 5. There is no heated filament to produce electrons. So, this is suitable for decomposable gas, but it is more expensive than hot cathode type. Cold cathode ionization gauge uses a high magnetic field as well as high electric field, about 4 kV between cathode and anode, to draw out electrons. High magnetic field around 1500 Gauss causes the electrons to move towards the anode. In case of hot cathode ionization gauge, we heat up the cathode to draw out the electrons, and it passes through a high potential difference. In case of cold cathode ionization gauge, I have the high potential difference, but I superimpose a high magnetic field. The electric potential is about 4 kV and the magnetic field that is superimposed has a strength of 1500 Gauss. So, high magnetic field causes the electrons to move towards the anode. So, as it moves towards anode, this will collide with the gas molecules that is present in the chamber. Chamber will be connected to the vacuum source which you are going to measure. So, as it collides with the electrons, as it collides with the gas molecules will be ionized, you measure the ion current and then it becomes same as measurement with ionization, hot cathode ionization gauge. Only difference is the electrons are emitted not by heating up the cathode, but I am superimposing a high magnetic field in a high electric field. Once electrons are produced, the measurement principle with hot cathode ionization gauge and cold cathode ionization gauge are similar. Anodes and cathodes are generally made of titanium. We can have different types of electrode geometry such as cylinders, plates, rings, rods. So, this is an image of this is a schematic of cold cathode ionization gauge. So, you have the cathode and you have the anode. So, you superimpose the magnetic field which is as high as 1500 Gauss. This chamber is connected to the vacuum source. So, this is connected to the gas whose pressure you are measuring and it is very, very low pressure or high vacuum. So, this magnetic superimposed magnetic field will draw out the electrons and then those electrons will collide with the gas molecules, positively charged ions will be formed, you measure the ion current is a measure of this vacuum. Next, we will talk about Alphatron vacuum gauge. This is a radioactive ionization gauge. This is relatively less expensive than cold cathode type, but this is also not hot cathode type, meaning this is a version of cold cathode type, but we do not use superimposed magnetic field to draw out electrons. What we do is we make use of radioactive material to generate alpha particles which will ionize the gas molecules. The typical range of Alphatron is 10 to the power 3 to 10 to the power minus 3 torr. The gauge size may be made very, very small. It may be as small as 12 centimeter cube, 12 cc. So, Alphatron vacuum gauge uses suitable alpha emitter to ionize gas. A positively biased electrode is used to collect only the negative ions that are produced by the impact with positively charged alpha particles. So, we use a suitable alpha emitter to emit alpha particles which will collide with the gas molecules and will produce negative ions. So, a positively biased electrode is used to collect the negative ions which are produced by the impact with the positively charged alpha particles, and this current will be a measure of the vacuum. Typically, as radioactive source, we use radium salt rolled into a gold foil for alphatron. Current generated is proportional to the degree of vacuum, and it is very small, of the order of 10 to the power minus 3 ampere to 10 to the power minus 9 ampere. Calibration differs for different gases. However, the calibration is fairly linear, which is an advantage. That the calibration is linear is true for all ionization gauges. So, this is a schematic for Alphatron vacuum gauge. This is the chamber which is connected to the vacuum source. You have the alpha emitter here. So, this is the radioactive source material. So, it produces alpha particles. These alpha particles collides with the gas molecules that are present, and the negative ions are collected using this ion collector. So, the current due to this is a measure of the number of ions formed, which is dependent on the number of gas molecules present in this chamber, because that decides the number of collisions, and number of collisions decides the number of ions formed. So, ultimately the current due to these negative ions is a measure of this vacuum. So, we talked about 3 different types of ionization gauges. All these ionization gauges have fairly linear output, which is an advantage. We talked about hot cathode type, we talked about cold cathode type, and we talked about alphatron. All these can be used for measurement of high vacuum. Care should be taken for hot cathode type, which has a disadvantage of possibility of filament burnout or gas decompositions, which are overcome in case of cold cathode or alphatron. But cold cathode is more expensive. It uses high magnetic field superimposed on the high electric potential difference, and in case of alphatron, it makes use of a radioactive source. So, we stop our lecture 27 here.